Hey guys and gals, welcome to another edition of Sin Hardware Tech in 10. Today I'm doing a technology intro on pulse width modulator design. And last one I did was basically how VRM works and what you need to know about voltage regulator modules to make a good buying decision, or if you just want to know. Today we're talking about something called a PWM, which is this little chip right there, okay? And you can see that kind of chip. There's actually more than one on every motherboard. That's because more than one thing needs a PWM. The digital PWMs, they all have a little dot on it. So this little chip has a little dot in this corner. This chip has a dot in this corner. And there's one more here. And these are all digital ones. There's also one analog one underneath this heatsink that provides power to the PCH. But so far on this board, you have three of them. You have a IR 3567. Now you can Google this and you'll probably find some of my reviews. There isn't a data sheet available on it. This is made by International Rectifier. It's a 6 plus 2 phase. Remember, this symbol means phase. Digital PWM. And you're probably wondering what the heck is the difference between digital and analog, which is one question I'm going to go into, and I'm going to digress the information that you need. And then we're going to talk about the phases needed on a motherboard to run modern systems. Alright, so IR 3567 is a 6 plus 2 phase digital PWM. And then these two PWMs are basically the same model. They're both IR 3570. Alright, and these are 3 plus 2 phase digital PWMs. On these PWMs, you see the plus and then you see a smaller number next to it. This smaller number is a secondary output. So a PWM can basically input two different types of things. This makes it, if you have a plus, the second number there is basically like you're using a second PWM to run those outputs. On a board such as this, X79, you have different outputs that need voltage. So the X79 platform requires something like 5 or 6 outputs, okay? So your first one is CPU V-core. Then you have two other voltage VRMs that you need for two different voltages inside the CPU. Number 2 is VCCIO. CPU V-core is also VCC. That's the technical name for it. VCCIO is basically the QPI / VTT voltage in the BIOS. And this is everything in the CPU that's not really, can be part of the memory controller, can also be part of the I/O, such as the DMI, the PCIe controller, stuff like that. Then the third one is VCCSA. On these boards, VCCSA is basically hooked up to the IMC, the internal memory controller, and thus is named such on Gigabyte boards. The fourth thing you need is this DRAM. These 4 DIMMs, they need their own voltage regulator, which is this single phase right here. So DRAM set number 1, and then 5 would be DRAM set number 2, which is over here, which has its own single phase. So this board has 6 phases for the CPU V-core, 1 phase for VCCSA, another phase for VCCIO, 1 phase for DRAM 1, 1 phase for DRAM 2. It doesn't matter which one, but they need their separate PWMs. You can't run these on their same PWM. Thus here, you need a total of 5 PWM outputs. Alright, and if you want to drive the PCH, you also need a 6th one for the PCH. However, they're doing this with a single phase analog. Sometimes you don't even need a true VRM for the PCH if you don't need variable control over its voltage. And in that case, you can use a linear regulator or something like that. But this is unimportant for the moment. Okay, so we can just forget about this. This is ran by a single Richtech controller, which is analog, single phase, mostly integrated stuff. Alright, so CPU V-core is running a 6 phase from that, right, like I said, and then only 1 phase of these two are used for the VCCSA. So VCCSA and CPU V-core, these are both using IR 3567, 6 and 1. Alright? Then you have VCCIO, which is QPI VTT, and DRAM 1. Now, these two are going to go off a single other controller, an IR 3570, and only one phase per each of these. So basically the 3 plus 2 is only really 1 plus 1. Okay, not a big deal that they're not using all of them. They wanted to make sure they digital control for everything that they advertise, such as their 3D, which basically means digital control for all the CPU voltages and digital control for both the RAM segments. So that's 3 digital. Actually, it's 5 digital, but they could have done 5. I guess 3D goes in with their BIOS and stuff like that. Then DRAM 2 runs off a different IR3570. So basically, a second voltage rail on the 3 plus 2 isn't being used, only one phase is being used. So you're not even using that second voltage rail. You don't have to use that second voltage rail. But there's a reason they have separate voltage rails, and here you'll see 3 digital PWMs. Not all their rails are being used, however you need separate rails for each and every single one of these. The feedback loop for the CPU VCC is much different than the feedback loop for VCIO and VCSA and DRAM 2. They need their own feedback loops. The feedback loop is what basically makes it happen. So let's go over what's negative feedback, right? Negative feedback is basically you send a signal, okay, and the signal is processed or used, and then you monitor this output, okay? Alright, so this output from the used or from the end source is going to be the input to your regulator. Alright, and this will be the regulator. And then the regulator sends a signal. And if you know in biology, you might know effector, stuff like that. So you have a regulator here, and you have the change mechanism here, and then goes to be used at the source. So basically what happens is you send a signal, let's say 1.5 volts, to the used, or to the source. The source takes it and it responds that it's only receiving 1.48 volts. Now that 1.48 volts is being monitored by the regulator. The regulator is going to be like, oh, okay, it's 1.48 volts, please add plus 0.02 volts. So it'll go to change, and this change will push the 1.5 volts to 1.52 volts. And so the output from the used will instead give 1.5 volts. And if it doesn't give 1.5 volts, then it'll keep adding voltage, keep adding power. So it's a feedback loop. But the way a negative feedback loop works is that the thing you put in, you want to go away and deviate. If you deviate from the input to the source, then then the monitoring is going to be different. So positive feedback means you're moving closer towards what you need, and a negative feedback means that the feedback is moving further away from what you need. Basically, all feedback loops are negative. In the human body, for instance, there are only 2 positive feedback loops, and if you're a male, then one of them is only going to apply to you. That is blood clotting. So you have a cut in your hand, then blood rushes with platelets and different clotting mechanisms and antibodies, and they'll try to clot the wound. As it becomes more clotted, they send more and more of these things until it's finally clotted, and then it stops. So it's positive feedback for much of that time when it's attacking the wound. Positive feedback, however, there's also one more thing, and that's childbirth. So when a woman starts giving birth to a child, they push harder, different types of hormones are released, different types of things, and they just keep adding on to each other towards a single goal. However, everything else is basically negative. So you grow hair, and when your hair grows too much, then you're trying to grow as less as you want, so it's going in the opposite direction. But basically, I just want to explain what a feedback loop is. So that has a lot to do with analog and digital, because in analog PWMs, the feedback loop is mainly analog, and digital is basically done like a computer, in ones and zeros instead of voltages. So basically, this is how many outputs we need on an X79 platform. Let's go back to C77, okay? So that's why you need the different rails for the voltages, because you need different feedback loops, and each of these have their own feedback loop that's separate on each PWM. So if you have 6, but this number of phases is just how many possible phases that PWM can output on each rail. Okay? Do you understand that? Z77 has one for vCore, just like there. It also has one for VCC-IO and one for VCC-SA. Then you also have one for iGPU, right? iGPU is not present on X79. And then you have one for DRAM. Thus, the same number, and if you want to keep digital, you have to have the exact same number of PWM here. However, on Z77, Intel specification says that you can combine these into one. So this can be 2 or 3, or these can be combined into one. So it gets a little bit more tricky with Z77, but you do have the added iGPU, so you don't have 2 DRAMs, you only have a single DRAM, but it's the same. So that's why you need different outputs. For instance, Z77 is a good example of how you want 8 phases total. You're going to have to use an 8-phase controller, and that'll be IR3563A. And that's 8 plus 0, right? Only single output, 8 phases goes here. Then you need a separate PWM, IR3570, to run this and iGPU. But then Gigabyte goes a step further and also gives you one more IR3570 for the VCSA and DRAM. Okay, so they don't combine these on the UP5, for instance. However, on the UD5H, they do combine these. But that's why a lot of manufacturers double 4 phases with 7 plus 1 or 6 plus 2 controllers or 6 plus 1 controllers. They will only use 4 of these, right? They'll only use 4 of them. And then they'll use this plus 1 for iGPU, because a PWM is much more expensive than doublers, right? So it's much easier to double 4 phases to 8 than it is to use a true 8-phase PWM and have to add a second PWM or a third or fourth PWM just to run your iGPU or your VCIO or VCSA. Even if you combine these two, there's still an issue. But yes, doubling is cheaper than adding a separate PWM, plus there are not many 8-phase PWMs. Especially in the analog realm, I don't know any 8-phase PWM. So, let me cross this out. Okay, now you know why phases are needed, and I've described to you how doubling can work and get 8 phases when you use one PWM that's less than 8 phases. I've done that last time. So phases needed, that's checked off. Now we need analog versus digital. So let's go over the basics, right? You saw that feedback loop I provided you last time. So let's draw real terms. CPU, right? And this will be analog, okay? This is typical, and this is how it was always done in the past, and this works very well even to this day. Analog. Here you have the VRM, right? So this includes the FETs, drivers, chokes, and capacitors, all that goody stuff. VRM is providing output to the CPU, right? This output to the CPU is monitored back in a loop. And then you have a PWM. Remember, the PWM connects with PWM signal to the driver. So the PWM's input, right? So that's the CPU, and this is the monitor. Now, you're going to monitor more things than just voltage in a PWM. You're going to monitor voltage, current, and temperature. Usually current and temperature are tied together, and they'll go into a current balance, temp balance, and that'll go into a processor. So in a modern PWM, I'm just going to draw block diagrams. Your monitor is going to come in. Then you have a reference voltage being fed, okay? So this reference voltage can come from the BIOS, and it'll come in here, and then it'll go to a block where it's intake. So this intake could be something like SVID protocol or DVID protocol, which are both digital. Now in analog PWM, SVID and DVID are converted through a digital to analog converter, a DAC, to analog signal. So this DAC is going to send a signal here, and then the monitor signal is going to come here. So this is your reference, and this is the real. The reference and real are going to be compared into something called an error amplifier. Can also be called a comparator. Okay. So this error amplifier is going to take the real signal and the reference signal and then give you out an error. This error is the difference between them. This error goes into something else, okay? So you also have something in the corner here, which is a sawtooth waveform generator, okay? And And this waveform generator is going to be giving out the signal that you want. So basically, this is also sent to here to process a correct waveform. I'll call this sawtooth. And this sawtooth waveform is going to want to help change the error into something that should be outputted and change to give the voltage towards where you're looking at. So then the sawtooth and this error are going to go into a digital not digital PWM, but a PWM modulator. Okay, the PWM modulator is what's going to give you the output to give to your PWM, to the phases, so it gives PWM output. Basically what happens is everything is digital, right? So this voltage is coming in, it's not being touched, it's being compared through hardware, and the difference is being given to a PWM modulator, which is taking input from a sawtooth waveform of how it should be going, right? So the sawtooth waveform is... Oh, that's very bad. Disregard that drawing. So basically this is being told what it should be, and it's all hardware-like, okay? So there are many pros to analog. As you can see, everything is in voltage and in the form that is being fed back and being fed out. PWM signals are in this form of a duty cycle and switching frequency. The switching frequency is the rate at which the MOSFETs will switch. The duty cycle will tell the driver how long to keep the high side fed on. The longer you keep the high side MOSFET on, the more voltage, the higher the voltage is going to rise. Because there's a direct linear relationship between the amount of time the high side fed is on and how much linearly the voltage rises inside the inductor. And that'll be determined by the duty cycle, okay? The duty cycle is responsible for voltage change. Switching frequency is responsible for many other things. So analog has a few benefits. First of all, it is fast. There's no delays. Okay, everything is quick. This is happening much faster than switching frequency. So if the switching frequency is 300 kilohertz, 300 times a second, this might run at 1,000,000 times per second, all right, or 500,000 times per second, but much faster because most PWMs have to be able to switch, giving out a switching frequency up to 1 megahertz or 1.2 megahertz, which is 1,000,000 or 1.2 million times a second. So this might be sampling internally at maybe like something like 2 gigahertz, 2 megahertz, or maybe 5 megahertz, or even maybe up to like a couple megahertz or a couple hundred megahertz, something like that. So this is very quick sampling. It's very fast. All hardware based, so no errors. Right? No errors. Okay? Fast, no errors. Basically, very easy to implement. Okay? So basically, it's also cheaper. Newer ones have digital pulse width modulators internally, or adaptive, but they're still not digital PWMs. And this digital in here just means that it's better able to take use of the sawtooth waveform and the digital to analog converter and all these input signals. It just makes better use of them. However, the comparison is still analog. This is analog comparison. Alright, so we saw the benefits. Now here's the issue, because this seems perfect, right? If your voltage coming out here is 1.5 volts and you need 1.55 volts, duty cycle will be increased to tell the high side MOSFETs to stay on longer so the voltage will go up. However, this is how it'll do it. So let's say you want 1.55 volts, okay? And current, this is what you want, and you have 1.50 volts. So the PWM is going to send a signal to increase the duty cycle. So that duty cycle will increase the voltage, right? And this would be the voltage, and this would be time. And this would be voltage. This is separate from this, okay? We can just move this monitor signal up here. So to move the signal, so right here it will be, you want 1.55, you're at 1.5. So you're at 1.5 volts, and here is 1.55 volts, and here's 1.56 volts, okay? So this is 1.56 volts, this is 1.5 volts, 55 volts, and this is 1.5 volts, okay? So you're going up. The duty cycle is in a plus right here. It's being pushed up. You're going up. You're going up. You're going up. You hit 1.5 volt. Then the signal is sent back. Oh, we're at 1.5 volt. Please go down. So then as soon as it reaches up here, the signal was going to turn into negative duty cycle. So duty cycle goes down and it goes down. Then you want to go back up. So it's positive here and it goes back up and it hits negative. Once it goes negative, it's going to go here and then it's going to go positive here. Please go back up. Negative here as it goes down. You see, the signal is always going up and down to provide you 1.55 volts. This will result in overshoot when you're going. So it'll go up and then it'll drop back down as soon as it's regulated. However, it's going to take a little tiny bit of time for the voltage regulator to react to the voltage being too high, and it might hit 1.56 volts. Do you see the issue? You have more possibility of overshoot. Your voltage output is not going to be as steady as it could be because it's always fluctuating, which is true of any voltage regulator. However, this is just going until it gets too high, then it goes lower. So analog PWM goes up until too high, and then goes down until too low. Do you understand where that issue might arise? Now here's what happened with the digital voltage regulator. Alright? Because they wanted to get rid of this need to keep going up too high and go down too low. You need to be able to calculate precisely how much, and that cannot happen unless the error and the difference is done in digital terms, in ones and zeros instead of steady state voltages. So we have the PWM here. Okay, PWM. So this would be digital. Then you have your VRM. Then you have your CPU. And then you have your monitoring. Remember, same monitoring, current, temperature, all that stuff. So SVID and DVID are digital signals. That's why in the analog PWM we use the DAC to convert them. So you have your inputs, okay? Then we have this monitor. This is coming in as analog single. It's a voltage. Alright, this is coming in as a voltage, and I'm going to make this box a little bigger. And when it comes in, it's going to go through ADC, analog to digital converter. That's going to give a digital signal up here. Alright, then you also have your ADC, you also have an analog digital controller for your current, your voltage, and your temperature is already maybe coming in digitally. Then SVID is also sending its signal, and they go to a digital processor. I'm going to put PID right here. PID is an algorithm, so instead of a sawtooth waveform, they're using algorithms. So this is going in here, and this digital signal is going to go into digital PID, the digital processor. Alright, the digital processor is going to take in other things such as current after it comes through its ADC, and also temperature, all going to be fed to a digital PID. Now the PID is also going to relate through other buses to the BIOS, stuff like that. So you have more things. You also have non-volatile memory in a digital controller, which is also going to react and give different profiles for different things to the PID. And then you have a digital pulse width modulator. Alright, it doesn't have to be digital once again, but digital pulse width modulator allows for more things because it's basically a computer. Digital PID will give the reaction to the pulse width modulator, and the PWM will send out a signal to the VRM. So basically what's happening, everything is being processed in the digital processor. You don't have an error amplifier and comparator, right? No more error amps. Your analog digital converter and SVID are being compared with an algorithm, and different profiles can be stored, and then different transients can be done. You have direct input from the user much easily. You have more control over OVP, OCP, OTP, and phase, temperature versus current. You have phase control, stuff like that. So this is over voltage protection, over current protection, over temperature protection, phase controls, which can be set to like extreme, and this will be like number of phases on. Temperature versus current, you see this in some ASUS BIOSes, and this can be set to basically ignore temperature for current, or to lower current if temperature is too high. So this is a balance mechanism. Then you also have switching frequency control, which is much easier to control. Then you have stuff like you basically control different angioms. You can control transients, speed. You can make it fast or slower, how the VRM reacts to things. So these are all different things digital PWMs have control over because of this digital processor and the non-volatile memory. Right? Your BIOS can convert with all these, and you can actually set these, which is much easier to set than with a resistor. Remember back in the days when we had a LLC that wasn't really LLC? We never had a thing called LLC. We had to do voltage regulator modification to the PWM. You had to put a stupid little resistor at these different pins or at these solder points to get out this result. That was because basically you were dealing with hard set values. You put a resistor at a certain value between pin FB, which is feedback, and pin ground or whatever, and then you would have this much droop, or you would eliminate this droop, or you would add this kind of droop, or you would remove over voltage protection, or remove OCP. Now that can all be done through a PWM digitally. Modern analog PWMs have also put this type of thing in, but they don't have non-volatile memory. They just have hard set things that can be controlled through a GPIO. Now, GPIO is a general purpose IO for analog. A GPIO is needed for LLC, DVID, and stuff like OVP, OCP. They can't really be controlled on the fly as easier as it is for PWM to be controlled. But here's the benefit of PWM. Since you have this algorithm, it can determine how high to go. Remember our same voltage versus time? We start at 1.5 volts and we want to go 1.55 volts, and this is 1.56 volts. 1.56, 1.55, 1.5. Your voltage goes up, duty cycle is plus. Same thing here. Duty cycle and switching frequency. Those are two main things that will be outputted. So same output, same inputs. Basically the chip is just different. You can have the exact same VRM components and an analog or digital PWM. The VRM components, MOSFETs, inductors, capacitors, drivers a little bit, but everything else has nothing to do with whether this is analog or digital. So this goes up just a bit. I've calculated you need to be on for 1 picosecond to hit 1.55 volts. So it's on for 1 picosecond, and then it's going, and if it drops, you can calculate how long until the amount of current needs to be replenished, and then you can go plus again, right? So you just keep going up there, and you stay much closer to this 1.55 volts because you're calculating at what time it needs to go over. Your result of overshoot is much less because you have calculated for how long to increase depending on different loading states. So it's a lot of very good, very tough programming that goes into digital PWM to make it perfect. But there's an issue. Digital has a lot of benefits, right? It has non-volatile memory to store things and for better control. Very good control. It also is much more precise, right? You know exactly how much to go. It's much more accurate as well. It knows exactly where the voltages are, it knows exactly where the currents are, it knows how to get to it, and it gets right next to where it should be. However, it also does much better with different transients. It can predict transients, right? So it can predict what's going to happen in the future, and it's going to act on those predictions because this sampling rate has to be fast. However, there's an issue. While this is fast, this used to be slow. Analog to digital converter caused delay. However, new PWMs, especially when Gigabyte adopted it, don't have this issue at all because the analog digital converters have a sampling rate that's much faster than the switching frequency, and thus gives it the ability to actually be effective. So now slowness is not an issue. So the analog digital converters are now fast enough, but that used to not be the issue. So 1 year ago, 2 years ago, 3 years ago, it's improved exponentially over the years, okay? So that's basically the difference between analog and digital converter and their pros and cons. So most modern PWMs are best done digitally, but digital PWMs are also much more expensive. You have so many more options, right? So, but there are ways to tell if you have an analog or digital PWM, and it's not by your motherboard's marketing. For instance, ASRock C77 Z77. All analog. Because they use ISL 6367, which is analog. However, they're lying and calling it digital because they are liars. But that just might be their marketing not being smart enough to know the difference. And basically, Gigabyte used Intersil PWMs for a very long time, and Gigabyte never called them digital, right? Never called them digital. You might be able to get away with hybrid digital, but true digital, you need a true digital PWM. There are only two major PWM manufacturers right now, or one, IR, International Rectifier. Right, International Rectifier, all digital. Chill is part of International Rectifier. Alright, so Chill is inside International Rectifier now. And all PWMs coming out now are manufactured and said to be International Rectifier. Alright, Intersil is analog. However, they are the most advanced analog PWM. But they're still analog because their feedback loop is still an analog. All right, that feedback loop is all what it's about, to be analog or digital. Analog or digital. All Gigabyte Z77 boards that cost maybe $130 and upwards are all digital. Same thing for Asus boards. MSI saying hybrid digital with their UPI semiconductor analog PWM. ASRock is lying and saying they're digital with their Intersil PWM. So it's a lot of give and take, and it's very hard to tell what is what. However, now I hope you know more about what the difference between analog and digital is. I also have a thing on my website. If you go to www.sinhardware, and then you go in the top menu and you click VRM articles. And if VRM articles, is analog versus digital. Also, how else do you know other than going to my website? I also have something called the VRM list. You can Google this, or you can just go to my website like I just showed, and it's actually on the top menu as well. Excuse me. The VRM list will show you what's analog and what's digital because I've put it there. I've also put their make and model of each PWM used on modern motherboards, including most, if not all, X79 and Z77 boards that are of interest, as well as some prior X58 boards, but not many of those. So I have a VRM list. There's also one way to know. In your BIOS, analog PWMs will have LLC control. Yes, both analog and digital. Digital plus analog. Check, both have this. Switching frequency. Okay? On a digital, you will have ability to set what frequency. Usually in 50 through 100 megahertz steps. Analog will usually be either one or two options. It might, on MSI I know it says 1.0x or 1.5x or 2.0x times the base switching frequency. That's how much you can increase it. So that might be available. OCP might be on both. Digital will be exact value or percent value. OCP on analog will be only a few values, so a few. However, because of the hardness to integrate through GPIO all these different things, digital PWMs will have OVP, OTP, right? All of these in actual percent forms or actual value forms. Such as on Gigabyte PWMs, you can set, on digital 3D BIOS, you can set 135 degrees Celsius as your OTP. Analog PWM, you can't do that. There's also one dead giveaway. Phase control. And it's not power savings or anything. It's the ability, such as extreme performance. You have maybe 5 through 7 options. You also have a fast response. So basically, if you have a menu in your BIOS that's riddled with all of these things, then you're most likely digital. However, if you only have maybe like a 3 or 4, then you're analog. So you can tell by your BIOS controls and the granularity of how fine you can control them, whether it's analog or digital. Of course, if you're really sneaky, if a company's really sneaky, they can do everything even with an analog PWM, and make it look like a digital PWM. However, they won't go through the trouble because, number one, that's very hard to do and requires a lot of programming and a lot of hardware stuff too. Also, digital PWMs use a smaller area and are much better for power density, right? So watts per centimeter cubed, that's power density. Power density is extremely important, right? So a digital PWM only has a few resistors and everything around it. Analog PWMs, however, have a lot more, and that takes up a lot of space on the VRM, stuff like that. So basically, you've seen what's up. Both of the types of PWMs have the same output signals, right? So they all have duty cycle and they all have switching frequency. But internally, the way they process information, the way they take inputs from the user, and the way they're all able to calculate or just do it through hardware makes them different. So if you're using a server, I'd prefer analog because analog PWMs tend to run a little bit cooler. Even the PWM on a digital PWM actually gets warm when it works because it's doing so much calculation. However, if you're doing overclocking or anything of the sort, or you want the best of the best, you're going to want digital. Analog is also a little cheaper. So that concludes this. I hope you know now about pulse width modulators. They're a chip, and I hope if you have any questions or comments, you please post them. Thank you for watching. Sin out.